So in this video, we're going to go over arc length and curvature. So if you remember back from Calc 2, we talked about arc length for normal functions, and then we also talked about it with parametric functions. So essentially, we're going to extend that concept now to if I have this vector function, can I figure out what the arc length is? So essentially, if I'm walking along this curve in 3D, what is the distance I would walk between points A and B? So just a reminder that we have smooth curves, meaning that the derivative is non-zero. We're only going to be able to define arc length for smooth curves. So just as a refresher, recall in 2D, we define arc length of a curve which our x had some function of t, our y had some function of t, and then our t varied between a and b as the following. The length of that curve was going to be the integral from a to b, and then inside we used our distance formula because essentially we chopped this up into smaller pieces, used the distance on each, and then we could show it rearranged to this formula. So inside was the square root of dx dt squared plus dy dt squared. Integrated with respect to t. And typically what would have to happen here is either the square root would completely condense, maybe you had to make a trig sub in some special cases, or you could possibly make a u sub after simplifying this. So you still have essentially the same kind of thing that's going to happen for us. The only difference is now we're not just dealing in 2 dimensions, we have vector functions in 3 variables. So when we're working in R3, we define arc length in an analogous way. So if we have the vector function r of t given by the triple x of t, y of t, z of t, where again our t is going to vary between some set values, say a and b. Then we define the arc length of the curve from t equals a to t equals b as the following. The length is still going to be an integral, and we're going to integrate with respect to t. So our bounds are going to be from a to b. And then when you extend that distance formula, you're able to rearrange things nicely. You get dx dt squared plus dy dt squared plus dz dt squared, integrated with respect to t. Okay, so again, very nice just extension of what we learned in 2 dimensions. And if you aren't 100% sure where this came from, again, it just comes from the distance formula when you broke down trying to add up something that had curves to it. So essentially the process was we had this curve in 2D. We broke this up into straight line segments. We approximated those using the distance formula, added them up, let the number of segments approach infinity, and it turned into this integral. Now for us, we're going to see a couple different ways that we can potentially write these things, purely because when we get to vector calculus, you're going to see this n quantity change. So if you've had me before, I am a very big stickler about making sure that you have your notation appropriate because this end of the integral is very important for us. So this is telling me that I'm integrating with respect to t. What I'm going to do now is show you another way that you can potentially write this thing. And then we'll see even more ways after we do a couple examples. So since we know the derivative of our vector function r prime of t is just we differentiate component wise. So it's x prime of t, y prime of t, z prime of t, or dx dt for this component, dy dt for the second, dz dt for the second. If you notice, we've got the square root of each of these components squared adding up. So really, this inside is just the magnitude of this vector. Okay, because remember, the magnitude is you take each component squared. So x prime is the same thing as dx dt, y prime is dy dt, and z prime is dz dt. We take each component squared, and then we take one square root. So instead of having to write this formula out, I can write it in a more condensed way because this is just the magnitude of the derivative of r. So ultimately, we can also write that the length L is the integral from a to b of the magnitude of r prime of t. Okay. So again, hopefully a nice extension. What you did in Calc 2 is going to be very similar. You might need to look up some of your integration formulas, especially like in this example, we're going to be working with trig functions. And then you're typically going to use u substitution, or hopefully that square root is going to disappear completely. Just be careful whenever you take a square root. Remember, you get the absolute value of that thing. So let's try an example. Let's go to a nice new page. We're going to find the arc length of the curve which is r of t, and it has components cosine of t, sine of t, and then natural log of cosine of t. Specifically from t equals 0 to t equals pi over 4. So before I jump into having to write my integral over and over and over, I'm going to find a couple things, and I'm also going to see if I can simplify that square root before writing the integral. So the thing I have to start with is I definitely need to differentiate this function. Okay. Derivative of cosine is negative sine. Derivative of sine is positive cosine. And then here, I'm going to have to use chain rule. So I get 1 over the inside function when you differentiate natural log. And then chain rule, I've got to now differentiate by cosine of t, which is negative sine of t. So add as many steps as you need, but at this point, you've taken a ton of derivatives. I trust you know the process for this. So just cleaning up that last component, overall it's negative, and then sine over cosine. I definitely don't want to leave it like that. Let's go ahead and convert it to tangent, and hopefully nice stuff will happen. Now I'm going to need to square each of these components and then take a square root. So we're going to go ahead and find the length of this vector, or that magnitude. So that would be the first component squared plus the second component squared plus the third component squared, all under a square root. Well, all that does is it makes these positive, so this gives us sine squared of t plus cosine squared of t plus tangent squared of t. And again, I'm going to have to integrate this, so I'm hoping that things simplify. And at least right here, sine squared plus cosine squared of the same argument is 1. So that is that main Pythagorean identity. And then hopefully you recognize this is also one of your Pythagorean identities. It condenses to secant squared. But if you aren't comfortable with that, I can show you off to the side. We know sine squared plus cosine squared is 1. That is just our unit circle. X squared plus y squared is 1. If I go ahead and I divide everything by, let's do cosine squared of t, well, sine squared over cosine squared is tangent. So that gives me tangent squared of t. Cosine over cosine is 1. That gives me tangent squared plus 1. And then 1 over cosine squared is exactly secant squared. And so that is our second Pythagorean identity. And then you could do exactly the same thing. You could divide through by, in this time, sine squared. And sine squared over sine squared is 1. Cosine over sine would give you cotangent, so that would be cotangent squared. And then 1 over sine squared is cosecant squared. So this works out nicely for us because it gives us the square root of secant squared of t. Okay. Now this is nice because yes, the square and square root do cancel each other out. But again, you have to be careful. It technically gives you the absolute value because the square root was something non-negative. So its output needs to be non-negative. When I go to integrate, I can't quite integrate with these absolute values. But what I'm going to do is I'm going to look at my values of t. 0 to pi over 4 would be quadrant 1 of that unit circle. And all of our trig functions are positive there. So since this is our bounds, I can drop the absolute values. So this is going to equal secant of t. And that is only because our secant function is non-negative for the interval, or t being in the interval from 0 to pi over 4. If I gave you different bounds, say from pi over 2 to pi, thinking of your unit circle, that would be quadrant 2, pi over 2 to pi. And in that case, the secant function would be negative there. So you would have to actually put a minus sign out front to integrate it. If you had bounds that crisscrossed, so maybe like pi over 4 to 3 pi over 4, you would then have to split it up at pi over 2 and do 2 separate integrals, because in one case the output would be positive secant, and the other case it would be negative secant. So you just got to be conscientious of those particular functions. But thankfully for us, because we're in quadrant 1, I can just drop the absolute values and I don't have to worry about splitting anything. So we are all set now. We have the inside of our integral. I can go ahead and actually find this arc length. So finally, the length of our curve is the integral from 0 to pi over 4 of the magnitude of the vector r prime of t. And we just figured out what that simplifies to, so we're going to integrate from 0 to pi over 4 of secant of t dt. Now you might not remember this integral right off the top of your head. That's okay. It's not one that's super necessary for you to memorize. It was kind of a funky one too. It's not like you could make a u sub like integrating just tangent. This one required you to multiply the top and bottom by something. So if you need some help, just make sure you have that integral list for some of those uncommon ones. So the antiderivative of this is going to be natural log of the absolute value of secant of t plus tangent of t. And then we're going to evaluate this from 0 to pi over 4, okay? So I do need to keep going because I have to get just a number in the end. Plugging in the upper bound, that is secant of pi over 4 plus tangent of pi over 4 minus natural log of secant of 0 plus tangent of 0. And evaluating these, secant of pi over 4 is the flip of cosine of pi over 4. Cosine of pi over 4 is root 2 over 2. So if you flip it, it actually condenses really nicely to just root 2. And then tangent of pi over 4, because sine and cosine are the same, that is going to be 1. And then over here, secant of 0 is the flip of cosine of 0. Cosine of 0 is 1, so its reciprocal is 1. And then tangent of 0 is 0. Okay. So if you left it like this on written portions of your test, not a problem. You can do a little bit of simplification here because this is really natural log of 1, and that's just 0. So it does condense a tad bit, and this would be the exact length of our curve. And again, if you left it at this stage, not a problem, but you do need to make sure that you're evaluating your trig functions. Now, the one thing you may not have seen, it just depends on the semester and who you have and the book you had. We can also talk about something that's called the arc length function. So instead of having to go through, if I have my curve, say here's my vector function r of t, I can pick a starting point A, and what I'm going to do, instead of finding an ending point that's exact value B, I'm going to assume that that ending value is a variable. What I can do then is then I can integrate from this starting value A up to T, and it's going to tell me the arc length for any ending value T, okay? So as long as I have a smooth curve, this is something that I can do this for. And in turn, it creates a function. So I would plug whatever value I want here to find my arc length. Say my starting value was 0 from 0 to 7, or 0 to 12, or 0 to 100. So it saves you the hassle of having to go through every single integral instead. So this is called our arc length function. So we're going to let r of t be a triple, which is comprised of x of t, y of t, z of t, for t being defined between at least two values, say a to b. The ending point can be whatever. So this is a function that is smooth. So we're going to let r of t be a smooth curve that is traversed only once. As t increases from A to B. The traversing only once basically guarantees you're not in that case of the unit circle, because you go around once, that gives you the arc length. But then if you go around twice, it's going to double that. So you want to make sure that the graph isn't just repeating itself over and over and over. So as long as we have this, then the arc length function is defined by the following. So we're going to call this S of t. S is what we typically use to represent a length. If you've taken physics, you see this represents kind of your position. It is going to be exactly our arc length formula, but instead our upper bound is going to be a variable. So I don't want this inside to be in terms of t anymore because t is up here in the integral. It would be a bad practice to put t on the inside as well, because then the variable's both inside the integral and in the bound. So instead we use a different dummy variable. I'm going to pick u, but again, you could pick any other letter that we haven't used. Okay, so this is defined where the value of t is between a and b. Okay, so I'm going to go back to this last example to kind of show you just what this is, because it doesn't do anything different. All it means is instead of having this as my upper bound, I maybe would put a t value instead. So I still take my derivatives exactly the same. I'll still get to this reduction here, but the only difference is instead of having my upper bound be pi over 4, it would be t. And then instead, I would just change this to a different variable, u. So in the process, not much else changes. Only thing that does is this first piece. So this would be from 0 to t, secant of u du, and it would just be used here, and you would just have an upper bound of t instead. And so we would basically end at that point. The arc length function would be natural log of secant of t plus tangent of t, okay? The only thing is I might have to restrict this from 0 to pi over 2 for my ending value, because after that, again, remember, it would make some problems here. So this would give me the arc length of this curve for any value between 0 and pi over 2. Because now it's much nicer if I want to find the arc length from 0 to pi over 4, I would just plug in t as pi over 4. If I want the arc length from 0 to pi over 3, I plug in pi over 3 here. So it saves me the hassle of having to go through this entire thing every single time. And in the end, it gives me just that function of t, okay? So nothing different, it just changes that upper bound. The reason this is important for us to define this function is because of this next notation we're going to go through, which leads into our next concept called curvature. So the one thing to notice here, if you remember way back in Calc 1, when you were going through one of the fundamental theorems of calculus, if I take the derivative and the derivative is in the upper bound, remember the integrals and derivatives undo each other. So what ends up happening for this arc length function is if I take the derivative, it's going to just cancel everything out, and this will get replaced by a t. So we actually come up with a new notation, okay? So notice, if I take the derivative of this arc length function with respect to t, again, it cancels the integral out, and it just replaces u by the variable we differentiated with respect to. Okay. So if you remember, the DSCT is that Leibniz notation, but it's representing a bunch of differentials. So what we can actually say is we will use the notation real crooked, sorry, that the change with respect to arc length is equal to the magnitude of r prime of t with that change in respect to t. Okay. So ultimately, we can write the following. Our arc length is the integral from a to b of the magnitude of r prime of t dt. And that inside is really the change with respect to the arc length, because these two are equal to each other. Okay. So this gives you a nice way to just write arc length instead. Of course, it's a lot of things going on, a lot of different notations, a lot of different variables, but this ds is basically telling you to integrate with respect to the change in the arc length. Here, you're integrating with respect to change in the parameter t. So in practice, in order to actually evaluate this, yes, of course, you're going to have to use this notation. But again, when we get to vector calculus, this concept's going to pop back up. So we have to recognize that there's this nice connection between the change in our arc length and that curvature, okay? So this brings on another concept now, which we're going to call curvature. So want to refresh on just some of our important vectors and then kind of talk about where this curvature thing is going to come from. So recall, for a smooth curve C, meaning the derivative or the magnitude of the derivative is not zero, with given vector function r of t, the unit tangent vector is given by t of t. It's exactly the derivative of r over the magnitude of that derivative. And just like tangent lines kind of gave you an indication as where the direction or where the curve was headed, it was like headlights if you're driving along that road. That's exactly what this unit tangent vector does. So the unit tangent vector is given by this, which helps indicate the direction of the curve. Okay. So visually what we've got going on here is we've got this vector function r of t that's being traced out. And then at any given point here, let's use this example, the unit tangent vector is going to be length 1, and it's going to give you the direction that curve is heading. So in that case, it would be here, down here, that unit tangent vector would point in this direction, and then over here, it would be something that's a little bit flatter, okay? So the unit tangent vector helps us indicate the direction. If I want to kind of figure out how much my curve curves, essentially, that's this concept of curvature. So what we're going to do is we're going to be concerned with this unit tangent vector and the rate of change of it. We're going to compare that to the rate of change of the length of the curve here. So if you think if they're similar to each other, the curve's not going to be changing much. But if there's a drastic difference from the way the tangent vector is heading versus how big that curve is, we're going to have something that has large curvature. So right up here, you can see at this point, it's changing directions. There's going to be a distinction between these two. It would be high curvature. But if I'm on a flatter piece, the rate of change that tangent's going to have, or the tangent is changing, is not going to be much. And also the arc length over those different intervals are not going to be changing much either. So we'd have low curvature at points like that. So we define the curvature of a curve C, which is defined by that vector function r of t, to be the following. Okay. We use the Greek letter kappa, which just kind of looks like a fancy K. and we're going to take the rate of change of the unit tangent vector over the rate of change of the arc length. And we're going to take the magnitude of this, okay? So again, this, just a Greek letter, it is kappa. Okay. So with this ds is thought of as the rate of change of arc length. Now you may be sitting here thinking, how the heck do I compute something like this? Especially because this is that Leibniz notation, so I have to take the rate of change of the unit tangent vector with respect to the rate of change of my arc length. And currently, I only know a formula for what my unit tangent vector is. I do have a formula for the arc length, but I don't know how to take weird rated changes like that. So what I'm going to do is I'm going to try to rewrite this. So this particular formula is very difficult to compute. As it currently is. But we can actually express this in terms of that parameter t by using chain rule. Okay. So remember, it's kind of like we have this intermittent variable. We know the unit tangent vector deals with the parameter t. I'm kind of adding an intermittent where I'm evaluating that unit tangent vector in terms of the arc length. So if I want to take the derivative of the unit tangent vector with respect to time, our parameter t, I can first go through the arc length, and then I'm going to go from the arc length to that parameter t. Okay, so that's exactly our chain rule. So I can really rearrange this to get this thing that's hard to compute. So the derivative of our unit tangent vector with respect to the arc length is really just the derivative of the unit tangent vector with respect to t over the derivative of the arc length with respect to t. This is just t prime. This, we've already figured out, is really just going to be r prime. So in my curvature formula, when I take the magnitude of this, it's the same thing as taking the magnitude of this. So in general, our curvature kappa is the magnitude of dt over ds, which we've rewritten as dt over d parameter t divided by ds over dt. And then you can take the magnitude of the top and bottom separately. The top, the derivative of the unit tangent vector with respect to t is just t prime of t. And then the bottom, the magnitude of ds dt is exactly r prime of t. So this gives us one formula for our curvature that we can actually compute. Okay. So let's try an example of this so it'll hopefully make a little bit more sense. And we're going to work with a nice shape. Let's compute the curvature of the circle x squared plus y squared equals a squared, where a is just a real number, and really a positive real number. So what I'm basically asking is, how much does a circle curve? And realistically, it's going to depend on the size of the circle. So if you have a small circle and you pick a point here, it's going to have to drop real fast in comparison to if I have a bigger circle. It is less curve over each of those equal spaces. So what I'm going to need to do is I'm going to need to find t prime of t and r prime of t, which means then I'm going to have to parameterize this curve, okay? Because my curvature is written in terms of a vector function. And right now, this is not a vector function. So I've got to come up with one that is a smooth curve. So here, since the curvature is defined in terms of a vector function, r of t, we need to parameterize the circle with radius a. So if you think of that, you know cosine and sine will get you on a circle. So you can use cosine of t, sine of t. This would be a circle of radius 1. If you put a 2 here, that would be a circle of radius 2. So for us, we're going to put that constant a out front, okay? And this will be my vector function that defines the circle. And specifically, you can restrict your values of t to be between 0 and 2 pi. That will take you around the circle once. But ultimately, you're going to see that doesn't actually matter for this example. Okay? So now that I have this, I need to figure out the derivative of my vector, and then I also have to figure out what is the derivative of my unit tangent vector. So I've got to find both of these things. So from here, r prime of t is not too bad. That is negative a sine of t, and then a cosine of t. Okay. We also are going to need the magnitude of this, so I might as well find it now. So if I take the length of this vector, that's just going to square both of these things. So this becomes a squared sine squared, makes it positive, plus a squared cosine squared under a square root. Well, you can factor out an a squared from both of those, and it would give you a squared times sine squared plus cosine squared, which is just going to condense down to 1. So this becomes the square root of a squared, and a is the radius. It is a positive number, so the square and square root do cancel. So I've got the piece that's going to go in the denominator of my curvature. Okay. Now I need to find t of t, but all that is the derivative divided by the length of the derivative, because I've got to make it a unit vector. Well, we found the length of r prime. It's a. So really, I'm going to do 1 over a times r prime, which is not r prime. I'm copying down r. So r prime is right up here. It is negative a sine of t, a cosine of t. Okay. So this is r prime divided by the magnitude of r prime. But all that does is it cancels out the a, and it gives us negative sine of t cosine of t, which is great because this is our unit tangent vector. And hopefully you can see that the length of this vector is 1. So I need to now take the derivative of this thing for my curvature. So this will be negative cosine of t, negative sine of t. So I need the length of the derivative of the unit tangent vector, which will be positive cosine squared plus positive sine squared under a square root. So this whole thing ends up equaling 1. So in general, my curvature is the magnitude of t prime of t over the magnitude of r prime of t. Well, it happened to be that our derivative's magnitude was 1, and then r prime of t is exactly a. Okay. For most curves, your curvature is going to depend on the point you're at. However, for a circle, it is symmetric. It's got that rotational symmetry. So no matter the point you pick, the curvature is going to be the same. And all it is dependent upon is the radius of that circle. So a circle of radius 1, the curvature is always going to be 1. For a circle of radius 3, no matter the point you're at, the curvature is going to be a third. The bigger your circle, the less it's going to curve over that difference of time. So I one time had a student long ago that told me, is this something that could be used to help flat earthers? Because the radius of Earth is so big that the curvature is essentially nothing. So you can kind of think of it like that, but no, the curvature is never going to be nothing. The Earth will not be flat as a result of that. But the bigger the circle, just like kind of we're standing on Earth right now, we're not going to see it curving because the radius is so big. So it's a much more gradual process. So the last thing we're going to do with this is we're actually going to come up with another formula for curvature, because maybe you've noticed if you've had to go through and find those normal vectors, the derivative of this thing can be really cumbersome. So it all just depends on the different question, what you're given, what's going to make sense for you. But sometimes you might not actually want to take this derivative. So I'm going to show you the process of how we come up with a second formula for curvature. And the nice thing about that one, it's only going to involve that vector function r. You're going to have to take 2 derivatives. You'll still have to do some algebra, and you'll actually have to take a cross product here, but it still might be simpler in some instances than having to find the unit tangent vector and then take the derivative of that thing. So this is going to be a little bit of a tedious process, and it's going to go through a lot of the stuff we've worked with. So try to follow through the best that you can. It's important for you to see where these things come from. But again, I'm not going to necessarily ask you to reproduce this. But you're at a stage that knowing why stuff happens is essential. And it's something that you need to be asking yourself and not just taking for face value. Some things I can't possibly do this for because it would be a 2-hour-long video to get through it. But at least in this case, it might be like 5-10 minutes for me to get through. It's worthwhile for you to see the applications of all of this. So let's try another method, okay? So depending on what we know about a smooth curve C, we have another way to calculate curvature. Since the magnitude of r prime of t is exactly the change in arc length with respect to the parameter t, and our unit tangent vector is exactly r prime of t over the magnitude of r prime, we can rearrange the second one. If I take the magnitude of r prime of t and times that by the unit tangent vector, it's exactly r prime. Okay, so that just comes from multiplying this to the other side. But this right here is exactly ds dt. So what I can do is really say that r prime of t is the magnitude of r prime times that unit tangent vector, which is the exact same thing as the rate of change of arc length with respect to our parameter multiplied by the unit tangent vector. Okay. Now, between these, all of them are functions of parameter t. This is a function of t. This is a function of t. This is a function of t. So what I'm going to do is I'm going to take a derivative, because hopefully what I'm going to do is come up with a new way so I don't need this piece up here. I want to rewrite what is the magnitude of t prime. Okay? So that's my whole goal, to just re-put that into, or put something else into my formula besides the magnitude of t prime. Okay. So what I'm going to go here, because I want to get t prime, is I'm going to differentiate all sides of this with respect to t. So again, right now I have r prime of t is ds dt, which is a function of t, times t of t, a function of t. I'm just dropping the of t part because it would make this even messier than it's about to become. So by taking a derivative, we get the following. Derivative of r prime is r double prime. On the right, you have two separate functions. The one out front is just a scalar function. T of t is a vector function. Still, if I'm taking the derivative of the product of these two things, I'm going to have to use my product rule. So I keep one and I differentiate the other. Then I add differentiating the first, keeping the other. Okay. So again, this product over here is going to be a vector function, but these right out front are scalar functions. So what I'm going to do is I'm going to take this vector and cross product it with this vector. Okay? Because again, my whole goal is, can I come up with what is the magnitude of t prime in a different manner? So ultimately, if I do r prime cross r double prime, r prime is the SCT times t. Let's see, these colors I haven't done. R prime is exactly this from up here. And then r double prime is exactly this expression I just found. So I'm going to cross product it with ds dt t prime plus d squared s dt squared, or second derivative of the arc length with respect to the parameter t, times t. Okay. So we're getting there. I've got to take this vector, cross product with the sum of these two things. So remember, one of our properties is that cross product does distribute. So this is equal to this first vector, cross product with the first component, and then I would add the first vector again, cross product with this second vector. Okay. Still seems really messy right now. That's okay. The nice thing that happens here is, if you notice, it is the same underlying vector. These are scalar functions outside, so you treat them similar to as scalars. So remember, if you take a vector and cross product it with itself, it gives you the zero vector. If you take a vector and multiply it by a scalar and cross product it with itself, that scalar multiple does nothing. It will give you the zero vector. So because these are both scalar multiples of each other, these are parallel vectors. So automatically, I don't care what this thing is, it is the zero vector, which does absolutely nothing for me. Okay? So what I'm able to do is I'm able to do r prime cross r double prime just by finding this piece. And then realistically, remember scalars, even scalar functions you can pop out, because this is the same scalar function in both of them. You can go ahead and factor that out. So this would be ds dt squared. And then the vector that's left over is t cross t prime. Okay. Now, if you remember, one of the properties that we went over was, if a vector has constant length, then it will be orthogonal to its derivative vector. That was a very special case. If you then think about it, this is the unit tangent vector. It is always length 1. It is going to be orthogonal to its derivative. Okay. So here, since the magnitude of the unit tangent vector is always 1, we know that the unit tangent vector and its derivative are orthogonal, which is why the unit tangent vector and normal vector are orthogonal. So what ends up happening if I go to take the magnitude of this, remember our formula is you take the magnitude of each separately, and then you times it by sine of the angle between them. But because they're orthogonal, the angle between them is pi over 2. This is exactly 1. And the length of this vector is exactly 1. So ultimately, when I take the magnitude of t cross t prime, it ends up just being the magnitude of t prime. Okay? So this is great because now I have another way to represent the magnitude of t prime, which is what is in my curvature formula. So let's tie all of this together now. If I take the magnitude of r prime cross r double prime, from back up here, it's just the magnitude of this. So this is equal to the magnitude of ds over dt squared times the magnitude of t cross t prime. But we just figured out the magnitude of t cross t prime will not depend on t at all. It becomes the magnitude of t prime. So this tells me r prime cross r double prime is really equal to the magnitude of ds dt squared times the magnitude of t prime. And t prime is the thing I want to solve for. So just rearranging this, the magnitude of t prime is the magnitude of r prime cross r double prime over the magnitude of ds dt squared. But remember, ds dt is just the magnitude of r prime. So really this becomes r prime cross r double prime over the magnitude of r prime squared. Okay? So all of that to get this other formula for curvature. So to calculate curvature, we have one of two ways. Curvature is found by doing the magnitude of the derivative of the unit tangent vector over the magnitude of r prime. But we just figured out this is exactly magnitude of r prime cross r double prime over the magnitude of r squared. So what ends up happening is you get the magnitude of r prime cross r double prime divided by r prime squared, but we already have an r prime in the bottom, so this becomes r prime to the third. Okay. So either one of these formulas is going to calculate curvature for you. And it really depends on the problem, which is going to be the more easy one to use. Okay. You might also have to find max curvature. So I'm going to give you an example where we're going to find the curvature of a function and then just explain to you how you can find the max, just purely for time's sake. Otherwise, this video would also be 2 hours long. So I'll do an example to kind of tell you or kind of show you how you can see which one's going to be the easier formula to do. Regardless, you have to find r prime first for either one of these formulas. And if you're going to find t prime, you need r prime anyway. So you might as well just start with that and then see where it goes. So let's do one example. We're going to find the curvature of y equals e to the x. Okay. So again, in order to figure out the curvature, I've got to have a vector function. So we need to parameterize this curve. So we can parameterize the curve by the following. Because it's a function y equals something in terms of x, the easiest parameterization is you let x be t. Your y is then e to the t. And since we're in 3 dimensions, I'm going to go ahead and add that 0 there because I might have to take a cross product, so I do need a 3-dimensional vector. So we can parameterize by this vector function, where this t is any real number because the domain of e to the x is anything you want. Okay. So then I need to take the first derivative, r prime of t. Well, that's just 1 e to the t 0. And I need the magnitude of this regardless of the formula I use. So the magnitude of r prime of t is first component squared plus second component squared plus third component squared under a square root. So this becomes 1 plus e to the 2t. Okay. So this is a really good observation for me to figure out what formula is going to be better to use. This does not simplify nicely. So if I wanted to use my first formula where I'd have to find t prime, you had to find t by taking this and dividing it by this. And that is going to give you awful functions because then I need to differentiate that, okay? So because this did not clean up nicely, that tells me my other version for curvature is going to be better to go through. But just to write that down so you have it, if we want to use the curvature formula where it's t prime over r prime in magnitude, we would have to differentiate this vector function. T is r prime of t over the magnitude of r prime. And so that is 1 over the square root, and then e to the t over this square root. And then the third component is at least 0. Then I would need to find the magnitude of the derivative of this thing, and that is messy beyond belief, okay? So if I want to use this formula, you'd have to differentiate this vector function, which would be messy. So because the magnitude of r prime does not condense nicely, I'm not going to use this formula for curvature. So instead, let's use that our curvature is r prime cross r double prime over the magnitude of r prime to the third. We have this, we have this. I need to figure out r double prime, and then I need to go ahead and take the cross product. So r prime, just to put it up here, is 1 e to the t 0. The second derivative is then 0 e to the t 0. So taking the cross product of these two, we do our I, J, K, 1 e to the t 0, 0 e to the t 0, and find the determinant of this matrix. So writing that out, we've got positive I, negative J, positive K. For our first one, we go ahead and cancel these. So that gives us e to the t 0, e to the t 0. For the second one, we ignore this, and we're left with 1, 0, 0, 0. And the third, we ignore this. We're left with 1 e to the t 0 e to the t. So finding each of these determinants happens to work out really nicely because this is 0 minus 0. So you get a big old nothing in the first spot. And in the same manner, 0 minus 0. So you get nothing in the second spot. And then finally here, this is e to the t minus 0. So the third component is e to the t. So this vector turned out super, super, super nice. So the magnitude of this vector is going to be 0 squared plus 0 squared plus e to the t squared under a square root. Well, all the zeros cancel out, and this gives you the square root of e to the t squared, which again technically gives you the absolute value of e to the t, but e to the t is always a positive quantity. So we just get e to the t, okay? So this is everything I needed. Our curvature kappa is the magnitude of r prime cross r double prime over the magnitude of r prime to the third. So the top is e to the t, and the bottom is the square root of 1 plus e to the 2t to the third. Okay, go back up there just so you can see it. It is square root of 1 plus e to the 2t. So you can see for this function, the curvature depends upon the point you're at. It's going to be different for each value of t. So something you might be asked to do is you could be asked to find the max curvature of this function. Well, this is a single variable function. So if you want the max, you would have to take the derivative, and then you'd have to find where that derivative is equal to 0 or undefined. This would not be a great function to do that with because you can see the derivative of this is not going to be pretty. Finding criticals of this function is also not pretty. But it is something that's doable for these types of things. So again, depending on the type of curve you have, the curvature typically depends on the position that you're at. So you can find the max by finding the max of the single variable function. So we're going to be utilizing a lot of this notation like the ds equaling the magnitude of r prime of t dt. We might not use the curvature formula as frequently in vector calculus, but it is something that is important for us overall. Because if something has large curvature, especially if you're thinking about like a bridge or a hill or a roadway, that can pose a serious issue. So we're going to be concerned with this topic in realistic applications, but it won't come back too much when we get to the end of the semester to do vector calculus.